Wow, what a spooky sound. If you captured that signal from one of the moons of Jupiter, would you analyze that as being random or regular? Let's take a look. This is Gerhard Schmidt's AVR simulator with a twist. Gerhard and I have been tic-tacking backwards and forwards about the possibility of capturing registers. And the reason I want to do that is to track some random number generation as part of the old 16-bit arithmetic series. So we've covered addition, subtraction, multiplication, but now I'm looking at generating 16-bit random numbers so that I can use the full PWM on the Paduk PFS 154, which is 11-bit. So, and learn something along the way too. So let's have a look at some code. If I go to something like this one here. So this is the code which sort of works, and you'll see why in a minute. So it's linear feedback shift register, which I'm using for the algorithm for the actual generating of random numbers. But I deliberately have chosen very poor polynomials, which if you do your own research, you'll see these are appalling, and we'll also see it in action as well. And then basically all I do is I load up the seed, which is just 2901, and I load up the polynomials, and then I just do what we've done before with generating 8-bit random numbers. And that is doing LSL, ROL, seeing if we need to do EOR on the result, and then just repeating. So rather than talk about it, let's actually run it. And the new bit for Gerd's work, actually, the sensational bit, is that if I right-click here, I can actually start a register list, and it'll output as a CSV when we're all done and dusted. So I'm just going to run this, and we'll just have a quick look at this. So we'll see 2 and 3 are the polynomials, and then over here, this is where the random numbers are being generated and being captured by the CSV file. So let's take a look at that CSV file and see what those random numbers look like. Okay, so here is the resultant file, and here's the captured registers R6 and R7. Let's just get a couple of columns in here so that we can manipulate some of that data, and we'll just widen them up a little bit so we can see what's going on. First thing I want to do is to concatenate those two registers so that we can go from the two registers to a 16-bit hexadecimal, and then if we go hex to decimal on that result, we should get, so we get the resultant decimal. Now, assuming that that's working fine, what I want to do now is do it for all of those values that we captured, which is around 16,000, and we'll just paste them in there. And then what I want to do is actually take that formula generated numbers and paste them back just as numbers. So if we paste numbers only, fantastic. Now I'm going to actually paste them into a text file, and then what I'm going to do is import them into Audacity. And the reason for that is because the human ear is very good at picking up cyclic regularity. So if you go and watch the film Contact, you know all about that. And whereas just looking at a bunch of numbers doesn't help. Although, if we look at a particular number, let's have a look at this one here, 31927, and you can see it's followed by 64109. So if I do a search, then if I do a search for 31927, I'll certainly see that first one, and I'll see the 64109. This is occurring here on line 14. If I go to the next time I see it, well, first I shouldn't be able to see it, but there it is on line 126 and followed by 64109. That's a bad sign. And if we keep going, this is just, and that's why those polynomials are pretty hopeless. Let's go and copy that data anyway into a just a normal text file, and then we'll import it and we'll see what it sounds like. Right, so let's see what this data looks like. So it's code, or values I should say. Let's go for a couple of standard settings: 16-bit, no Indianness, one channel, and import. Now, you won't be able to hear what this is until I overdub it, but I'm just going to play this for me, and I'll put that sound over the top for you at some stage as well. But what I want to do is, it does sound a bit regular, but make it more of that regularity if we change the speed. And oh yes, I have to select the sample first, and then we'll go to change speed. And so I'm taking it from about 1 second out to about 10 seconds, and I'll play this again. And you can hear the regularity. And in fact, if we zoom in a little bit, let's do that. So we will view right in. And yeah, you can see the repeats that we saw in the numbers there. So what we're going to do now is have a look at different polynomials, better polynomials, and also better code. Right, so this is exactly the same code as we looked at last time, but these are recommended polynomials for 16-bit generating of random numbers using LFSR. So 13 for the first poly and 24 for the second poly. So pretty much just do the same thing, assemble, capture the code, and watch the numbers fly. Let's look at those numbers. Okay, so here are these numbers in a text file now. We could do the same thing as we did before, actually, and just check to see if there's any regularity. So I got 3991 there, followed by a 61967. So let's do a search for the 3991, and oh, that's a 63991. Let's go to previous. Yeah, there it is. So 61967 is what we're looking for. So we'll go to next. That's not the same number. That's not the same number. That's not the same number. Oh, this is very promising. So actually have not had a 399. There it is. And that's the one right at the top. You can see it's reverted right back to the top here, line 74. So yeah, that's looking much more promising. Let's get it into Audacity and have a listen. All right, here we go again. So 16-bit, no Indianness, mono, yep, looks good. And what does it sound like? A lot more random, strangely. But let's expand it out. And let's go again to, yeah, we'll go to 1 second to 9 seconds and listen to that. Yeah, that's pretty good. And if we just have a look at a small section of it, and we can have a look and see what it looks like. And yeah, not much in the way of regularity there either. So that's pretty good. But could it be better? Let's have a look at throwing a spanner or two in there. Okay, so here we are with the spanner version. So same polynomials, but this time I've set up 2 spanners to throw into the mix. And what this is going to do is after 23 counts, then a spanner is going to be thrown, a 7 is going to be, I think, added. And then that will start the second counter for the second spanner. And 37 spanners later, a second spanner will be thrown, and this time as a subtraction. So just have a quick look at that code. Everything else looks pretty much the same. And then we get down to the checking the spanner. So basically there's decrementing the counter, throw the spanner if it's at 0, and the only requirement here is that when the spanner is thrown, I don't want the result to actually be 0. So it's going to branch if it's a 0 down to here, but otherwise it's going to move it back in there and alter that that number. Do it all again for the second spanner, and anyway, let's not go too much into that. That code will be on the blog. Let's have a look at it and see what it might look at. or look like, I should say. So we'll capture the registers, and then we'll just step through this and see what it looks like to start with. So there's our original numbers, there's our better polynomials. Here's our count, so that's 17, which is hexadecimal 23, and 25 hexadecimal for 37, and then away we go. So we actually start that. Now we shouldn't really see anything. Let's just run this through. We shouldn't see anything until this gets down to throwing the first spanner. So let's just watch it click down here. 3, 2, all right, and then we'll step through. There's 1. So there's a exclusive OR happening there. And then we'll do that last one. Okay, so now it's got down to 0, so it's not no spanner. Now we should move this value, which is 56, into register 16. So let's do that. So there's the moving, okay, and then we throw the spanner, which is a immediate subtraction of the spanner number. So let's do that, and then you can see it goes to 4F, and then we're going to say, okay, so 4F is not 0, so we should be able to move it back, so that 4F will move back into that R7, and there it goes, and then we're off and running again. Now, because we've thrown one spanner, this 25 will now reduce to a 24, and then we're back. Save the registers, back to the start. Let's set this delay to 1 and see if we can't see that happening again. So all right, here we go. Let's step through the code. So we're making a random number, shifting and rolling, and then there's an exclusive OR, and we return. Let's do the subtraction, yes. So okay, that's good. So we throw the first spanner. It's non-zero, so we move it back. We do the subtraction of the second spanner, that's also 0. So now for the first time we throw the second spanner, so we move R6, which is 1D, into R16, and then we do an immediate subtraction of a negative number, which is an addition. So that becomes 20. 20 is non-zero, so that it gets moved back into our R6, and we're off and running again. Let's see what those numbers look like. Well, I've just put these numbers side by side. So this is our original no spanner numbers here, and you can see that if I pick something like line 14 here and I go across, there's no difference between those two. So no spanner has been thrown at this stage. Not until I get down to this point here. So here the R7 value has changed from 5.6 to 4.7, and then of course the numbers after that will vary as it goes through. So by the time we get down to line 29 here, the original no spanner was a number 10,519, and this is the new one 9,375. And we'll pick a likely number, let's say 9375. Okay, so search 9375. And what we're looking for is the 17702 afterwards. So there's a 9375. Do we see any more? There's a 9375 on that list, and a 19375. But I think we'll find, yeah, just our original one. So pretty good. Let's load it up into Audacity and see what it sounds like. Okay, let's import our 16-bit. No endiness, just mono, please, and import. And we'll see what that sounds like. Pretty random. More random than the other one, I'm not sure. Let's also expand that to 10 seconds and okay. All right, let's see what that sounds like. Not too bad. Let's zoom in a little bit. Let's try this area here and zoom. You're not picking up any patterns at all there, which is pretty good. Let me just go back out again. And I might also, while I'm here, just lower that pitch a little bit because it's a bit hard to pick up. So let's drop that down by 50%. Let's see what that sounds like. Yep, sounds like Morse code really, doesn't it? Let's drop it down again. Should be quite low now. Yeah, I'm pretty happy with that. Okay, so the next thing to do is to try and encode that as part of our PWM on the PFS 1544. What's all this about? Having a nice fake candle. Crazy, huh? That's the circuit working. See you next time.